In this video, we'll discuss the importance of OpAmp noise performance in sensing applications. You might be working with an analog sensor for industrial equipment, or you might be monitoring current in a battery-powered device, or you might need to amplify the output of a photodiode. All of these are sensing applications, and the noise performance of the OpAmp has a big impact on the measurement's accuracy and precision. To show what kind of a difference a low-noise OpAmp makes in the real world, we have a demo of ROHM's LMR1802GLB. On one side of the board, we have ROHM's LMR1802GLB, and on the other, we have a standard OpAmp. In this case, it's ROHM's BU7241. These sets of LEDs will light up based on output level. The green LED indicates the signal is within a defined range, while the red and orange LEDs light up when the output exceeds certain threshold values. While the standard OpAmp is fine in many cases, this demo will highlight the difference between it and the low-noise LMR1802GLB. The demo is set up so that the output will be 3.3 volts plus or minus 2,000 times the sum of the offset and noise. So ideally, with zero noise and zero offset, it would be 3.3 volts. With that in mind, we can demonstrate two advantages provided by the LMR1802GLB. The first is noise. You can see the green LED stays lit for the LMR1802GLB, while the standard OpAmp is all over the place. We can also see the difference on the scope, with the LMR1802GLB being much tighter, with a delta of 18 millivolts on its output. Compare that to the output of the standard OpAmp. And I've got it stopped so I can find a range here. And we can see a delta of about 52 millivolts. This is because the noise density of the LMR1802GLB is significantly lower than typical CMOS op-amps, and is actually similar to or better than that of bipolar op-amps, 2.9 nanovolts per root hertz at 1 kilohertz, and 7.8 nanovolts per root hertz at 10 hertz. But since it's a CMOS op-amp, you still get all the benefits of CMOS: low input bias current, low supply voltage, and low power consumption. Another important factor in minimizing measurement error is the input offset voltage. As you can see, the standard OpAmp is showing an output of approximately 1.05 volts. But remember, ideally it would be 3.3 volts. So you have a total offset of 2.25 volts. The LMR1802GLB, though, is coming in at 3.27 volts with an offset of just 0.03 volts. And remember, that offset is based on the input offset, which is multiplied by the gain, which again is 2,000 in this case. For input offset, the LMR1802GLB is spec'd at 5 microvolts typical and 450 microvolts max. That's about 1/4 the input offset of a conventional op-amp. Besides the noise performance, I mentioned that the LMR1802GLB, being a CMOS op-amp, provides some benefits over alternatives such as bipolar op-amps. Input bias current is rated at half a picoamp. It can operate from a 2.5 to 5.5 volt single supply, or plus or minus 1.25 to plus or minus 2.75 volt dual supply. And it consumes about 1.1 milliamps of current. It also offers a best-in-class 68-degree phase margin and can drive capacitive loads up to 500 picofarads. To learn more about ROHM's LMR1802GLB, visit rohm.com.